Right, this is the last type, FRQ 4. Here we are given a circuit. There is a switch that is initially closed. There's a resistor, capacitor, and there is a constant current source. And in this branch, a I constant is flowing over here. Now at t equal to 0, the switch is opened, and they are asking that a long time after the switch has been opened, the rate of change dV over dt of the potential difference across the capacitor. So delta V is the potential difference across the capacitor, and they are finding the rate of change of voltage uh, across the capacitor. It approaches a constant value. So they are saying whether that's a positive, negative, or a zero value. And they are saying that if the positive charge is on the top plate, then consider the voltage to be positive. Okay, see, this is RC circuit, right? Parallel circuit. And after all, if it reaches a constant value, we know that a long time would mean that as t approaches infinity. So when t approaches infinity, the capacitor is fully charged. The capacitor is fully charged, which means that the relationship Q is equal to CV. This Q becomes constant. C is anyway constant. So this V will also become constant, which means that the change in V with time will just become zero because V is not increasing anymore. So the answer will be zero. Right here, they're asking us to derive a relationship, but not to solve, for dV over dt, where V is again the potential difference across the capacitor in terms of RC, delta Vt, and some physical constants. All right, the switch is already open, so this is the circuit that we are following, and I think I'm going to use KVL. Let's assume that this current splits first off into two parts where I will be using KCL. So let's say this current is IC, which is going to the capacitor, and this current is IR. Probably if I'm starting with KCL, I'm going to say that I constant is equal to IC plus IR. That's first equation. And then I'm going to write KVL. So for KVL, I'm going to say that change of voltage across capacitor minus change of voltage across the resistor is 0. So change of voltage of capacitor is change of voltage of resistor. I don't think so I'm going to change this because that's something that I need anyway in the derivative. So let's call it delta V because that's what they are calling in the question. Change of potential of the resistor is just IR as per Ohm's law, and IR is just IR times, the current across the resistor is just IR. So IR times R. I'm not going to touch delta V here. R remains as it is. And what is I? IR is just as per the KCL. It's I constant minus IC. Right, so this is delta V is equal to R times I constant. And what is I? I is nothing but dq over dt, right? Because I is the current passing through the capacitor, and that is equal to dq over dt, where q is the charge on the capacitor. So that's how it looks like. So now delta V will be equal to R times I constant minus d over dt of q, and q is nothing but c times delta V, right? That's a formula, q is equal to cv. So delta V will be equal to R times I constant, I'm just opening the distributing R, minus R times, and this d over dt of c delta V remains as it is. C comes out because that's a constant. So delta V is equal to R times I constant minus RC d delta V over dt. I think that's my answer because they just wanted a relationship, a differential equation, for, I think it would be a better idea to isolate this. Yeah. So let's rearrange this. So R C dV or d delta V over dt comes on the left side, and R I constant minus delta V is on the right side. If we divide both sides with RC, then that's going to look like RI constant over RC minus delta V over RC, and this R and R is actually gone, crossed out, and we are just left with this much, which is our final answer. Finally, they're asking that if this resistor is now removed and we just leave a gap over here, then as per the differential equation we just got in the previous part, what is now the value of dV over dt shortly after the switch is open. That is 0, a non-zero constant value, or value with increasing magnitude. So the mistake that usually the students might make over here is they might think that R is 0, but no. If you are removing the resistor and leaving these terminals open, it is actually an open circuit. An open circuit means that resistance approaches infinity. So in this equation, if R approaches infinity, clearly this value will be delta V over infinity, which is 0. So d delta V over dt will just be I constant over C. Because had R was 0, then it will look like a short circuit. If it is connected, replaced by a wire, then R is 0. But no, if it's just taken off and the portion is just open, R is infinity.